Okay, well, I don't know if you can hear me all the way in the back, but if you can't, let me know. Welcome to tonight's program, everybody, and most importantly, welcome back after the summer break. I know that it hasn't been an idle summer, and there's been a lot going on, but it's always nice to get together again, get back to the monthly speakers, and have an opportunity to have something to do on cloudy nights, even though tonight is not one of those nights through the fall and winter, because we're going to have a few where this is where we really get to enjoy astronomy because the weather doesn't cooperate with us. If you don't know, I'm Dan. This is a meeting or a speaker for the Royal Astronomical Society of Canada, Victoria Centre. If you are just curious about being a member or are new, please look up the group. We have a fantastic website with resources and information about all the benefits of joining. And with that, I'm just going to kind of hop right in to what's coming up for tonight's program, which is, of course, to say that we're going to do an overview of upcoming RASC events. Hopefully some of those will be up at the Victoria Centre Observatory on the Hill and potentially a Plaskett night if the weather cooperates for us. Reg is going to be giving a Victoria Centre Observatory update, letting us know all the successes that they have been able to achieve, because it's been quite the litany of triumphs coming from the telescope, from he, David, and the crew. David Lee is going to do a session or a quick talk on what's up in the night sky. And Chris Gaynor was going to talk about what's up in space, because if you were up early and saw the announcement from NASA today, and then some of the media coverage, there's been yet more discoveries that indicate the potential of ancient life on Mars. Chris is going to talk about that at an upcoming Astro Cafe, because there's a concern that he won't make it to tonight. And I don't want to take that one away from him, because I don't think that there's anybody better in the society to give a good overview. And then Kirsten will be giving an introduction to our illustrious guest speaker, who's our own Dave Payne. So that's just a brief overview of what's coming up for the session tonight. After the talk is done, you're of course welcome to join for coffee, tea, treats up in the 4th floor of the Elliott building, which is just across the parking lot behind us. And I hope you have a wonderful time. Thank you.
Thanks, Dan. Okay, so I'll just give a quick summary of some of the upcoming RASC events. Just a reminder that we have Astro Cafe Monday evenings at 7 p.m., and that's either by Zoom or in person at the Fairfield Community Center. We have, there's a star party up at the Center of the Universe this coming Saturday, September the 13th. And just a reminder, unfortunately, Lori Roche isn't going to be able to come to this meeting tonight either. But she just wanted to remind people that we still need RASC volunteers for both the RASC welcome table and also for telescopes in the parking lot. So that's just a reminder there. We have our next monthly meeting here up at UVic on October the 8th. And there'll be more information about that coming up on the website, but it's a really interesting one. We're going to be doing a screening of a documentary called Northern Star, which was recently aired on CBC, but it's a really amazing documentary about John Stanley Plaskett and the observatory, and also some of the history of Canada's role in major space accomplishments. It's actually a great documentary. So there's going to be guests, Nick Versteeg and Bob McDonald are going to be here at the next monthly meeting, and it's going to be a really great night. So hopefully we'll see a lot of people here. And then lastly, just for member information, RASC is putting on part 2 of the NOVA program. So introductory astronomy information for new amateur astronomy and astronomers and people interested in space. That's going to be held up at the center of the universe for this session. And that's going to be on Thursdays, September 25th to October 23rd. But my understanding is, and it's great, the subscription to that is it's already full. So that's really great. So I think there may be another. Lori told me passed on that there might be another. Part 1 might be redone in the spring. So that's something to look for next year. Okay, so, and then just a reminder about the coffee and cookies, and then I guess there's Reg and David. So, Reg, did you want to say something about the VCU?
Well, hello, good people. There are some people that are new here. They're not aware that we have a wonderful resource at the Victoria Centre. We have a land sharing agreement with the NRC. We have our own little telescope, our observatory up in the hill called the Victoria Centre Observatory. And to partake, you have to be a member of the Active Observers Group. And it's very easy to do. And if you're interested, Chris Purse here will get you on the list. So what does that allow you to do? We have a 20-inch obsession. We have a 12-inch Dobsonian telescope. We have a research grade 12.5-inch scope and a really high quality Takahashi 5-inch refractor on a really good mount. And we have a very good state-of-the-art camera for astrophotography. And so what this does is a lot of people trying to get into astronomy. We buy a book called Backyard Astronomy, a famous book written in Canada. But the problem is they can't afford a backyard, they can't afford the gear, and the gear is really complex. So the Victoria Centre Observatory is a resource that eliminates those speed bumps and allows you to capture data and go up to the hill where they have nice dark skies and share the experience with others. So there's not only beautiful skies, you learn from other people and you enjoy fellowship. And so if anybody's interested, come and talk to me later and I'll give you a bit on that. But this summer it's been the best that I can remember because we had beautiful clear skies without smoke until late August. And so we have had so far this year 17 sessions up there, and there will be more. And as we have a session come up, there will be a message sent out to all of the people who are on the active observers list. If you have a gate time, you can come and join us, go up the hill, and have a great time. So I hope to see you up there. Okay?
Okay, so David, did you want to
Yes, thank you.
do your talk?
Well, yeah, good evening, everybody. How many people got out this summer to observe? I hope all of you. Yes, I've seen many of you out there, so I know you have. So what I thought I would do is just tell you where we're at. We're at the autumn equinox. So what does that mean? So basically, we're at equal day and night. Where's my little control here? Oop. There. Okay. So yeah, so that marks a time when the sun crosses the celestial equator and we get equal hours of day and night. So that also means our days are getting longer, which is good for us. I think the thing that we hated most about the summer was we couldn't really start until quite late. So that's going to change. So how many people got to see Saturn this summer? Anybody? Yeah. What was funny about it? Did you notice anything funny? Edge on, yeah? Okay, so yeah, we had edge on stuff. Somebody asked me up at the hill, like, how often does that happen? Well, commonly every, I think they say 13 to 15 years. I couldn't remember this date, but I looked it up and I did take an image in 2009. But prior to that, I was in Australia in 1995 and I saw it edge on. And I thought, well, that was the only time. But then I looked and obviously I did it in 2009 as well. So here we are, 13, 15 years later, edge on again. And I think it was edge on in March sometime. So the thing about opposition is Saturn's coming into opposition, so that means it's going to be bigger and brighter. So this is the time to look if you haven't already looked. And yeah, and November, the rings are going to start flaring again come November. So the other thing, which is kind of neat, is Neptune's nearby. Now, I know some people have attempted this. Kevin, you tried, right? At the star party. You managed to find it? Oh, great. So Neptune is a little bit on the dim side, so just so you know. But during the opposition, I noticed that if you have a wide field eyepiece on, say, a short refractor, you're going to be able to see it in that field of view. 5 degrees. Anybody, how else can you get a 5-degree field? Anybody else know? Jill knows the answer to this question.
Yeah, but you can't see Neptune.
I know. Yeah, binos, yeah. Well, you might, I wonder, has anybody actually seen Neptune with binos?
But no, it's quite dim.
Oh, yeah, it's got dim, but you can perceive it though, right?
Yeah, Brenda was great at finding it
Oh, okay.
last summer.
So you can do the same thing that Brenda did. Yeah, if you want to see it any better, obviously you're going to need more magnification, but even then, it's still a bit of a dot. And my understanding is that it's kind of greenish blue. I've probably only seen it a handful of times, and a lot of people talk about the blue images. Apparently, they weren't correct. So it is kind of a tealy green-blue color. Would you agree, Brenda?
Yeah, and it's just kind of like it's a disc. It doesn't treat it.
Oh, okay.
So, you know,
Underwhelming.
well, it's not, you know, it's not the color or that doesn't behave.
Okay.
Underwhelming or overwhelming depends on what you're looking at.
Yeah.
If you think about it. I'm not underwhelmed. Yeah, I've seen it with binoculars. But it's not. I wasn't underwhelmed when I saw it at all.
Okay. Try it if you wish. Okay. So the last thing I'm going to talk about is minima of algol. So what does that mean? Algol is a type of star which is variable. So variable stars, there's lots of variable stars in the sky. Variable stars either are intrinsically variable, in other words, on their own, they can actually change their brightness by either shifting their outer surface. Sometimes, and this is an interesting one, sometimes some stars have very large sunspots. So when they turn, they dim, right? When they face with their sunspots, they will show that. So that's called intrinsic. And the other one, which is what algol is extrinsic. And extrinsic just means that there's another player involved. So in other words, there's another star involved typically that causes the dimming. So in this case, it's an eclipsing binary. So you can see a picture here. Picture of an eclipsing binary. So you can see the dips. If you look along the graph, you can see there are these dips. So what happens is it is a certain brightness most of the time, and then it will shift. Now, algol is the poster child of variable demo because it's the easiest one. It's just under 3 days. So if you time it right, some people say if you time it right, it's the right part of the year, you can see it bright, dim, and return to brightness. But it has to be a particular time. It's easier to do it over a couple of days. So be easy on yourself, do it in 2 days. What I like to do is I look for the minimas. I'll show you how to do this. So first of all, where is it? So I'm sure most people can find Cassiopeia, which is the W. If you watch Cassiopeia rise, you'll see a string of stars. That is Perseus, actually. And you'll see like 3 stars that are stacked vertically. The middle one is brighter than the other 2. It's called Murphak. But from there, you can see, this is unfortunate, the scale of this diagram is not very good. But trust me, if you were to look at this in a star map, you will see that to the right of Murphak, that set of 3 stars, you'll find Algol, okay? And the whole idea behind doing this is we're going to do photometry visually. We're not going to use a fancy camera or anything like that. So it's actually quite possible to do photometry with your eyes. So how do you measure the change? Well, these stars that are marked in blue, and I have them in a table as well, they are reference stars. So Algol has a range of brightness between 2 and 3. So there are stars nearby that you can look at to compare. So when it's in its bright state, you look for the star, the comparison star is very similar, and you keep watching. Maybe the next day near the minima, you will observe it and you'll see it will shift brightness to one of the other stars, right? So that's how you're going to do it. So here, this is differential comparison. So those are the stars, and those are the magnitudes. And at its brightest, it is 2.1, and then it'll dim down to 3.4. So you can see it's quite easy. If you use these stars, they're very, very close to the targets of either the bright state or the dim state. So here are the dates. I suggest the 19th. Some people might suggest the 22nd. I guess that would work as well. 2:23, I know you guys are not early morning astronomers. Well, maybe I'm wrong. Are you early morning astronomers? No, you're shaking your head. Oh, Alex, I know you're an early morning astronomer. I've seen you do it. Okay, so this one's good. I think Jill suggested this one at 11 o'clock. You could easily see the minimum state. If you come back the next day, for instance, 10 hours will have elapsed. It'll return to its bright state. So you can just keep that in mind when you look.
David, what's the period of time between its bright and minimum?
2.97 days.
It takes, that's the recurrence, but
Yeah.
from going from bright to minimum.
Oh, I see. I see what you're.
How much time do we have to observe the minimum?
It's a couple hours,
Okay.
right?
So 11, if we started watching, looking at 9,
You might be able to see it.
be able to see it.
You might be able to see it brighter. The only reason why I say it's probably not a good idea is dawn's coming. So it may shift your perception a little bit, right? 11 o'clock is dark time, right? And if you wait long enough, you're going to start hitting dawn light, and that's going to kind of mess you up a little bit. Safest way is just the next day. So if 10 hours have elapsed, then you know you're good. Okay, so that's a strategy. It takes 10 hours, a day before minimum. That's what I'm suggesting, and then you note the difference. And if you want to, like I said, the next night, just go out the next night, and you can check it out again. That's it. Any questions? Yes.
How far apart are they physically?
How far apart?
How far apart are they?
Oh, the eclipsing binary? I don't know. I'm sorry. Dave is absolutely right, and I will measure his fingers later to tell you. Yeah.
So how long before they rotate around each other then?
It takes 2.97 days end to end, right? 2.97 days.
Days?
Yeah,
They've got to be really close then.
probably, yeah. Yeah, probably. I mean, I'll tell you, the eclipsing binaries are interesting, But I'm actually still waiting for T Corona B because it's a recurrent nova and it's going to blow up, right? I mean, cataclysmic stuff is more exciting than revolving things, right? Right, Dave? No, you don't get right.
Sorry, my mind isn't with you.
Yeah, go ahead. Question?
I looked it up, it's 2.978 between the two.
Oh,
2.698, sorry.
oh, there you go. We don't have to rely on Dave's fingers now. That's good. I don't know if there's anything else that's topical. Just get out there. Reg, are we moving into an okay part of the year or a not okay part of the year?
I think we got some good days ahead of us. Tomorrow night looks pretty good. After that, a bit dodgy. There's an awful lot of forest fire smoke in the interior of BC, and I hope it stays there. But it could leak onto the coast.
Well, anything you can do to take care of that, we would appreciate it.
I'll work on it.
Okay.
I have a question, David.
Yes.
I noticed you mentioned Beetlejuice in your presentation. What's the latest on that?
Well, Beetlejuice is interesting because is it intrinsic or is it extrinsic? Okay, it is called a pulsating variable, right? So it's doing it on its own. But interestingly enough, the last time it really dimmed, it was because it burst, there was a big burst from it, and then it created a cloud or something, a dark cloud, and it covered it. So is that intrinsic or extrinsic?
So the latest is it's a double star. There's another.
Oh, I heard that too, yeah.
Yeah.
Yeah, could be. There's all sorts of secrets in the universe.
Be a supernova sometime soon,
Well, they believe eventually one day Betelgeuse will blow up, yeah.
but not anytime soon.
Yeah, not in our lifetime.
Could have already happened.
Yes, you're right. You're absolutely right. It's so far away, it could have happened already. It's old news. All right. Good. Thank you.
Great, thank you, David. Okay. So with that, it's my pleasure to now introduce our guest speaker. So we're just going to do a laptop switch here. And I'll get my antiquated mouse set up out of your way. Okay, so while Dave is setting up his presentation, I will just do a quick introduction of David Payne. So David is going to be doing a presentation called How Friction Creates a Galaxy's Spirals. And David is a retired engineer, scientist, come astronomer, astrophotographer, and gardener, living it up in the far reaches of Vancouver Island. He loves to share his astrophotography and has been a member of the Victoria Centre of RASC since 2020, including hosting the astrophotography special interest group meetings. So in his talk, a scientist from another mother brings a multidisciplinary approach to this question that incorporates dissipative friction forces, thermodynamics, free body mechanics, and even chemistry to the nonlinear dynamics involved. So with that, it's my pleasure to hand it over to David Payne.
Thank you. Well, thank you all for coming. Give my wife a relief from me talking to her. So that's much appreciated. Gary asked that I introduce a little bit more of my background. I know it's not popular around here, but I am an oil and gas guy, born and bred, I guess. So I had an opportunity to work in all parts of the world, all parts of the business, and everything from a research research scientist to an executive and an advisor to the board and all that fancy jazz. So I've used a lot of the science that you're going to see in my business, in my career. And one of the things that I share with astronomy is that it's all about remote sensing. In the case of astronomy, the only thing we can do, the only way we can interact with what's out there is with light. When you're thinking of an oil reservoir deep underground, you don't get any light, so you have to rely on sound as interpreted by a geophysicist. You have to rely on remote sensing properties that you have to get by putting some sort of sensor, various things, down a little hole, a mile or two down the ground to get a really small sample of the properties of what's down there, and your imagination. So a lot of this, a lot of astronomy has in common with that is your remote sensing. You can't touch and feel and walk around space. And I'm used to dealing with that. So the other thing is I'm used to proposals, and I was a technical advisor. I do have a bachelor's and a master's, and my boss at work called me Dr. No, because as business people are prone to do, they'll imagine something, doing something, and when you say, well, that's either physically impossible or that's very unlikely to work, here's why I got the reputation of being called Dr. No by her chairman. And I would always get to say, that's not Dr. No, it's Mr. Anyways, so on to the talk. So this was how friction creates a galaxy spiral. And it's one of my purposes here is to talk about friction in space, or as for fluids, it's called viscosity or viscous drag. There's all sorts of words that you actually hear nowadays, like ram pressure, and those are all words that disguise viscous friction. In my other role, I will talk about spiral galaxies. I'll be showing a lot of pictures. The pictures you see are mine, taken from my backyard. It's such a fantastic hobby. If you're into it, or if you think you might be into it, join our special interest group. There's details on the website. Love to talk about it. But I'm going to talk about spiral galaxies in particular. And there's some in here. There's some other kinds of galaxies in here. But this is, in this figure, this is my favorite spiral in this figure. Is that pointing to the right spot? There's no pointing. That guy right there, my favorite spiral. This is the what cluster of galaxies. Most of what you see in these are galaxies. It's kind of my backyard version of the deep Hubble deep field image. That's what it's called. So I'm going to talk a little bit about if it's the same stuff, why is it so different? Some relevant, Richard Feynman is one of my favorite persons to quote after a few people, Adam Smith. But anyways, the one I want to focus in here, I think they're all relevant to what I'm talking about tonight. The one I want to focus in his mind, he was a physicist. He said the most remarkable discovery in all of astronomy is that the stars are made of the same atoms of the same kind that we have here on Earth. And I really take that to heart. So when I'm going through, what I like to do is interpret my photographs to figure out what's going on. When I'm going through, I'm always looking for, is that something that we see here on Earth? And as I take photographs and I try and figure out what's going on, I also read what the astronomy community thinks. And I go back to my project reviewing days and I go, that's not what's going on. So you don't really know what's going on. And to me, there's two things that can lead to. They're either unicorns or black swans. At one time, both were thought to be mythical creatures, right? Unicorn was a mythical horse with a horn on his head, some capable of flying, some not. And black swans were these large aquatic birds that swans are normally white, and they got this S-shaped throat and this little funny beak. And someone says, well, all swans are white. And people didn't believe it, they never saw it. Until Australia was opened up, and lo and behold, there was black swans. So in hindsight, black swan is a mythical creature, it was one time mythical, but after, you say, yeah, why not? Why shouldn't there be black swans? And if you look at the picture, I didn't bring one, if you look at the picture of a black swan, it was exactly the swan, except it's black. So here are some, what I believe are unicorns that you may have heard. And I'm going to try and convince you that these are unicorns. They all have to do with the spirals of the galaxy. So one is gravitational collapse of clouds into stars. Has everyone else heard that? Okay, well, you think twice. Gas in space acts like an ideal gas. So that's saying there's no friction in space. And I'm going to convince you that if you drop a stone and a feather at the same time, the stone will always hit the ground before the feather. Whether it's on Earth, whether it's on the moon. Now the moon is pretty close to zero viscosity. We'll get into that. But everywhere else, pretty much everywhere else in the galaxy has more viscosity in the atmosphere than on the moon. But the other thing that's professed is the spirals aren't material. They're either a magic gravity wave, as our simulation proves it to be, or also described as a cosmic traffic jam. And this is because, you know, we're talking about the winding problem with spirals. Spirals are thought to, well, could be on their own to just wind up. And the spiral galaxies are really disks. They're not really spirals, they're these, the spirals are just this, I don't know, optical illusion almost. And the only thing to explain the galaxy's rotation is dark matter. Now, I'm going to give you some suggestions about leading to dark matter. I haven't done a complete analysis of dark matter, but it is something that is not necessary to explain the rotation of the galaxy. The other thing I talk about is blind spots and shortcuts. And this happens to everyone in the scientific field. And it really takes people from outside your field to say, hey, you have a blind spot. You haven't looked in this corner yet. And that can really advance science. It's just someone from a different field looking at your problem and saying, you just didn't see this. You just didn't see you had a blind spot. And that's what I'm going to try. And we all take shortcuts, and sometimes shortcuts lead to these blind spots. So I'm going to try and offer some better explanations that come down to a change in your paradigm. So I better get on to this. So this is the first unicorn I want to slay. It says a gas cloud can become so large that it will collapse under gravity, and it says that if the cloud reaches something called the Jeans length, then it will collapse under gravity and form a star. The fact is, gases, by definition, gases will always expand to fill their container. Full stop. It doesn't matter. You have to have a container or it will keep on expanding. I'll show you that in a second. So gravity can actually only contain a gas from within. And that's because gravity only sucks. It doesn't blow. Very simply. Now, we still unconvinced. As for the paradigm shift, let's go on. So there's two paradigms going on. Astronomers are firmly on the right-hand side, and what I'm used to in thermodynamics is something on the left-hand side. Now, the problem with simulation is it can't hold both these views at the same time. So in this one, you can see gravity and momentum, our angular momentum, are at play here. And it assumes sort of planet-sized and planet gravity type materials. So in the left-hand side, there are collisions, and you can see this in this big yellow ball. It forms a random walk process. It is entirely unpredictable. If you want to go after any one of the balls or anything, there's so many collisions going on. And an assumption, if we assume this is an ideal gas, and these little black balls are molecules, that all the collisions are 100% elastic, so there's no energy loss when they bounce off each other. It's unpredictable except in some macroscopic properties. On the right-hand side, this is entirely predictable if you have a computer that's big enough to track each one of these particles as it moves through space, because it obeys the laws of angular momentum and gravity. The other rule they put in this particular simulation is when they bump into each other, which is quite often in this simulation, they amalgamate so that everything gets added to one another and they form individual bodies. And this one's predictable. And back in the day when people were doing astrology, that predictability was very important. And astrologers, if they wanted to make their money, they have to be able to do those predictions. And so a lot of the math went into, we can predict the solar system, we can actually look in the stars and say this star is going to do this at this period of time and all this stuff. And the model actually works extremely well, and probably the highlight of the model, I can't remember whether this is M13 or M5, but I'll show you the next one later, is tracking all these stars, and you can show this is a stable formation. Now, stars won't collide because they're so small compared to their space. Even though there's a lot of stars in those images, this is a globular cluster of stars. And these stars are all rotating and orbiting each other in this gigantic dance that they do, just like that simulation I showed you. So at some things, and here's another one, and you can actually see, I'll zoom in on that cluster. You can see all the stars that are in this cluster. Pretty fantastical. What the model doesn't do is tell you what happens to the stars if they do collide. You'll see some blue stars, a lot of blue stars in here. Most of them are white, but you'll see some blue ones. Blue are very young stars. These are ancient, from the beginning of the universe, clusters. We didn't make them in the galaxy. They came from outside the galaxy. They got trapped in our galaxy. But the fact that there are blue stars means something empirical has to be done that describes the state of stars that has nothing to do with the overlying model. If you start talking about how stars behave, then that requires some empirical stuff to be added on to the simulation. Now I want to go on the left-hand side model. Here's a simplified version of that. And some of the things, we can't track and never will be able to track a decent sized gas. There's just far too many of these individual points moving around. Now, if I freeze frame that, you wouldn't be able to tell what the next vision of that will be, giving any reasonable length of time. And if you've got too many stars, there's no way you can tell. Your best guess at where the stars will be next is where they are right now. So we have to model it with some emergent properties. One of them is temperature. And temperature is the average kinetic energy of each of these little blobs. I don't know what the mass is of them. I'd have to study this closely, but we do know what the temperature is, which is mass times velocity squared. We can figure out what the density. Now this is the density of particles. I don't know anything about their mass necessarily. I can tell what the density of the particles is. I can talk about the container itself. Each of these walls of this container are going to feel the momentum of the particles hitting it. And that's the pressure. And they're all related through this ideal gas formula, which you probably learned in chemistry class. But it relates the pressure times the volume of this container. So how much force is felt on the walls and the volume of that container is the number of particles in it. And this is a Boltzmann constant, but most chemists use R, which is basically Avogadro's number, which is the equivalent of a dozen for chemists. Bakers use a dozen eggs. We chemists happen to use an Avogadro's number of little particles. So really this ideal gas assumes that the particles don't collide, and that was based on the fact that the dots themselves take up some volume of the container. This is a 2D. So this guy named Van der Waals said, well, I'm going to correct my equation here if I'm going to allow them to collide. So there's a little correction that has to take place on the volume, which we ignore. And the other thing we have to assume is that the collisions were 100% elastic. Now, one thing that does emerge that I haven't talked about, and I will just briefly mention it, is dispersion. So these dots get scattered. You see the red dots get scattered throughout the volume. Even if they started really close to each other, they eventually get scattered around the volume. So for neutral, if we say these are neutral atoms in a gas, and we neglect any repulsive negative force caused by electron orbitals. I'll talk a little bit in a second now. The gravity will always be less than those electromagnetic forces. So if we neglect those electromagnetic forces, we can also neglect gravity. And so for any real gas, you can always ignore gravity. So now I'm starting to bite into this gravity collapse thing. For neutral atoms, collisions, we neglect those attractive repulsive forces. There's no stickiness, there's no nothing. And if you look at one of those Newton cradle things, you can see they made them out of hard steel. Those are as close to elastic as we can get. And that's why when you start that pendulum going, keeps going. Now, this guy named Joule, back in either the turn of the 18th century, late 1700s or early 1800s, he did this experiment, and it's a very illustrious experiment in thermodynamics. So he took a container, and he took a gas inside that container, an initial pressure, and that gas was at initial volume. And he put this all in insulation, and he let this gas expand into another volume. Okay, very simple. And we can calculate what the pressure is before and the pressure is after, based on the volume before and the volume after. If it's done really slowly, in an ideal gas, the temperature should be constant too. So it's an isothermal and what they call adiabatic, no heat change. And there's this other parameter called entropy that is a very important parameter that will come when you do steam. If you look at a steam engine or any engine that you want to look at, or any thermodynamic process. And you might have heard of it as the disorder in the universe is one way of looking at it, disorder. It always has to increase. And we can do a calculation to see what, using an ideal gas law, and here's the equation we got for entropy. And it's got the logarithm of the final volume over the initial volume. And if the final volume is bigger than the initial volume, this is greater than 0. Means entropy is greater than 0, which means this will happen. If I leave this for a day and come back, you'll never find it. All the molecules on the left-hand side again. Because that'll be a violation of this entropy rule that says it must be greater than 0. So basically, if you had the gravity collapse of a cloud, that would violate the second law of thermodynamics. And you don't mess with the law, so thermodynamics wins. Okay? So it can't go backwards. The other things that's worth doing is just taking a look at the consequences of the ideal gas law. One is, if I increase the pressure, the volume will increase, or volume will decrease. And so I can make this piston go up and down by, takes work, but putting some weights on this piston here, and then taking them off. So this is me doing work. It's not a reversible process. So I have to put work into the system. The other thing I can do with that system is heat it up and cool it down. Heat it up and let it cool down. Now, this is also doing work on the system to make it expand when it contracts. This is the work that's done by the heat of the flame in this case. So if you can imagine James Watt thinking about this, he goes, well, what if I put some burning coal and I make this steam and I take some mass and I throw it in here and I heat it up, the steam will become vapor and the vapor will expand. And if I stop it from expanding, it'll just keep its heat, right? And I can pipe that over to this side and let it expand over here. And I can actually lift some weights with that steam. And that's basically how a steam engine works. The entropy goes up because I can never get that energy that I lost the flame, lit the flame, like that work of that flame, I can never get back. It's lost to somewhere cold. So getting back to astronomy, how can I make a gas collapse? Right? Well, instead of adding heat to it, I can take heat out of it. I can do that by throwing some dust on the left-hand side of this container. So the heat that's in the gas will go bump into the dust particles. The dust can emit infrared radiation into a really cold space. That's at 4 Kelvin. That's as cold as it gets. So as long as I can do that, this gas will contract, the pressure will go down, and gas from this side will flow onto this side. And if I can get close to this very, very cold space, I might actually get the contents of this to actually condense. And this is a thermodynamic system that's consistent, that allows the contraction of gas. And that, I propose, is the way that stars are nucleated. Because I need a star to actually be a condensed material, because as I alluded to, I need some gravity from within to pull that cloud in. And that nucleated frozen stuff, if I get the size of the Earth, you can see it pulling more hydrogen in and actually growing to a star. So this table took a lot of work to put together. It's in the astronomical data. It's not my data. It took several AIs to ask, because astronomers are not used to presenting this stuff. I wanted to say, what is the temperature, the particle density, the pressure, all these thermodynamic properties that I can find throughout the galaxy. And the ones that I've highlighted in yellow here, these are the spiral arms, and everything else below it is the gaps between the arms and around the stars. So there's a couple of things I want to point out, is right in the dense core of the spiral arms, the dust gets the temperature down to 6 to 12 Kelvin. That's well below the critical point, which is essentially the condensation point of hydrogen. So either hydrogen condenses, or it acts like a supercooled fluid, which is almost the same thing. Okay, this next, and one thing, this area, most of the hydrogen exists as hydrogen molecules. And you'll hear that term, molecular cloud, because that's where the hydrogen exists as molecules. And this next part, in the gaps, in most of the gaps, the hydrogen exists as monatomic atoms. And the monatomic atoms are in a state where they have released most of their energy as kinetic energy. When the atoms come together to form molecules, they can store a whole bunch of energy in their bond. And the reason I'm saying this is hydrogen at these temperatures and pressures act just like water molecules for us. They're little devices that can store energy. When you make water cold, it has low energy. When you boil it into steam, it's got lots of energy tied up in not its molecular structure, by the fact it's a vapor versus a liquid. The next thing, the next area, this is ionic. So here most of the hydrogen is in ion form. And in fact, you can see the temperature is much higher, get up to millions of degrees. Where we sit in the solar winds, we're kind of in between this warm ionized medium and hot ionized medium. So if you go out into outer space, the particles have a lot of kinetic energy. Their temperature is really higher. You don't feel it in your spacesuit because it's so low density. So out here, you can see the density of particles goes up by a factor of 1,000, 10,000 into the molecular clouds. That's important too. So we've got the change in hydrogen, we got the change in clouds, we got the change in mass, we got the change in so it's actually a little bit, because this is so much colder, the pressure is lower where the stars are forming than it is in the gaps between spirals and where we are in the solar winds. So I think that's about it. Oh, one more quick thing here on this table. I hate showing tables because they're boring. But anyways, most of the roughly half of the mass of the entire galaxy is in these gaps. The arms themselves, while they've got about 50% of the mass, they're only between 1 to 5% of the space. So the gaps are much bigger than, I think that's intuitive, the gaps are much bigger. That gives you an idea of how dense, relatively, things are. One more thing about this model, I just want to say it is a very universal model. And I'm just going to touch on some of the things. It's used to, basically this model is used to solve the Schrodinger equation. So this is the kind of model. It is a universal model. It's used in control theory if you're an engineer at all. It's used in finance. You might have heard of the Blackman School's option pricing model. It's used there. And the other thing I'd just like to touch on, like I'm just on the edge, we're sitting here going, okay, there's this dark energy that's needed to combat gravity in order for the universe to expand. And everyone's trying to figure out that. They're trying to use, you might have heard of MOND, which is a change in gravity that everyone's trying to figure out. And I'm just wondering if it's a paradigm shift that you need to make. Because if we look at a random walk for some particles, you see over time in 3D space, they will go farther and farther away from each other. There's that gas expansion again. And it'll form a normal distribution, statistical distribution of where they are relative to where they started out. This is a natural expansion of space. Now, I'm not trying to prove this today, I'm just trying to say that when I look at where galaxy clusters are, where the mass is when we look out into outer space, kind of looks like a random walk process to me. And note that because these galaxy clusters are so far apart, the gravity between them has got to be really small. So back down to the really, I just want to touch on why I can ignore gravity in a gas. Sort of ignore gravity in a gas. If I take two atoms, there'll be a proton in the middle, and there'll be electrons orbiting the outside. And often when I say molecules have friction, people say, well, the molecules are too far apart. And I think the fact is, okay, if you make that argument, that van der Waals forces are too far apart, you can't also make the argument that gravity forces them together. And the reason is, both charge and gravity forces vary with 1 over r squared. And if you assume the electrons are on the outside of the atoms, and the charge forces we know are huge compared to the field of gravity. And in 1/r space, if you converted the forces, you would see these electrons being slightly closer together than the center of charge, means that for these neutral atoms, it goes for almost any atoms, there is a net repulsive force. And because these van der Waals forces, as we call them, that's what we call this force, after the guy who did the non-ideal gas stuff, the net effect, when you include gravity, is net repulsive force. So if I'm ignoring a repulsive force, I can't then not ignore gravity. The other thing you really learn, it doesn't take much temperature before each atom is way beyond the escape velocity relative to any other atom. It's always true, unless you're getting really, really close to absolute zero there. So one more thing to slay this goose, and it's Newton's shell theory. And it is an important theorem, and but it's been misunderstood or misused. So basically it says, if there were a gas cloud, just gas, any point outside will feel the gravity of this gas as if it was a point mass right at the center. Does that make sense? If the gas was a sphere. And what they do is they calculate, and there can be gravity between bodies of gas. In other words, an atom can feel the gravity from a bunch of atoms as a collective, but it can't feel the gravity of another atom. What this means is a single molecule can feel the gravity of a big bunch of gas from the outside, but something funny happens as soon as it goes into a sphere. It can't feel the gravity pulling out because it balances on both sides of the sphere, no matter where it is in any sphere. So the problem with Jean's length is if I take that down, if I enter this mass, it starts entering the sphere, it only feels the gravity from what's within the sphere, the mass that's within the sphere. And as I take that mass and I approach it to the center, that sphere gets smaller and smaller and contains much other gas until it gets either 1 or 0 in that sphere, and it can't feel the gravity from that, and therefore the pressure in this magical sphere has to be 0. Well, if the pressure is 0, that means the gravity, if the gravity is 0, means the pressure has to be 0. And then you can argue that if there was any higher gravity as I moved out, well, that gas would flow under that pressure gradient to the center. Okay? But then it can't feel more gravity because it can't feel any of the gas that's on the outside of it by the same Newton shell theorem. So you end up saying that the pressure everywhere in the sphere has to be 0. Well, that's not the case. The flaw in this is it assumes that you've got a static, circular, spherical gas cloud, which cannot exist because we already showed that it's always expanding. So the gravity, the force of gravity, always has to be less than the pressure on the circumference. Pressure is omnidirectional. gravity is only in one direction. Pressure blows everywhere. Gravity can only suck. Okay? So, Jean's theorem is actually being called Jean Swindle, not my name, but that's what a lot of call it. It's used to create stars and still preach this gravity collapses preach, but it is in fact the unicorn. That was a lot of effort, but it'll all come together, I promise. Okay? A little bit of a diversion, and it goes back to that entropy. And I'm not going to go through this step by step, I'll let you read it. But initially, Schwarzschild in 1916 proposed that black holes were a singularity. And when I learned about black holes, because I know about thermodynamics, I went, that doesn't sound right to me. Singularity is a very special thing. That means there's mass in a spot that has no volume, zero volume. And Schwarzschild based this simply on a gravitational model and showed that if gravity came too much, now couldn't do it on a gas, you have to have some sort of condensed material to form a black hole. But anyways, I'll talk about that in a second. This was a possible unicorn for me. I didn't know enough, but I eventually went on my own life. And apparently in 72, 74, I'll give the excuse that I was only 11, but two guys, Bekenstein, I don't know his first name, I can't remember, and Stephen Hawking, showed that, hey, if things fall into a black hole, that means the entropy goes down. There's something wrong here. You're violating that second law of thermodynamics. And they showed that a black hole had to have entropy. And if it had entropy, it had to have a temperature. And if it had the temperature, it had to radiate in space, radiate to space. And it had to jiggle and move. You can't do that if you don't occupy any volume. And actually came up with this formula. It's called either the black hole entropy or the Bekenstein-Hawking entropy. People debate that, I don't know why. And there's that Boltzmann constant that we saw before in ideal gas, and there's a new concept called the Planck's length in here. But anyways, this started a whole bunch of physicists doing the dance. Somehow we've got to amalgamate gravity theory with quantum mechanics, with thermodynamics, and all this stuff. And it's like string theory and all kinds of stuff that I have no idea what they're talking about. But this part, I fully understand. So how do I do this? This obviously works for some situations. This obviously works for other situations. So this is something that humans have the capability of doing, is holding two different concepts in your mind and figuring out which one you need to apply. In this one, a similar thing you do when we talk about the wave character of light. We know when to call it a photon, we know when to call it a particle, we know when to call it a wave, and there's a little bit of difficulty of reconciling those things because we don't experience that in our everyday life. But we're able to hold that concept in our mind. That's something that simulation models really cannot do. Okay? That Brownian motion with all this electromagnetism, it takes a kind of simulator called the finite difference where we grid up space and we grid up time and we put all our math in and we let it go. This is what I did my master's basically in, is finite difference and a bit of finite element simulation with this new solids, but that's what I did. Astronomers use what are called n-body simulations, just like that concept on the right. It grids time into increments, but it tries to track the particles. So instead of discretizing space, you keep track of particles. And the problem is, these simulators can't do both at the same time. And I've seen this, because it happened in my industry, is if the simulator shows it's going to happen, then it's going to happen. And I see this wording all over the place. Numerical experiments. A simulation isn't an experiment. It is you. A simulator can only tell you what you already know. And you already have to know it to put it in the simulator, so it does that. So there is no such thing as numerical simulation. In industry, you learn this lesson through bad economic decisions. We followed the simulator. We did something called CO2, enhanced oil recovery. And there was tons of money spent on this, as the simulator said it would work. It would work on little core samples. The physics said, well, it should work. And sure enough, when we built the simulator around the physics, it said it should work, but we got some things wrong. And the nature of the simulators, when we implemented it, didn't work. Now, very difficult to see in something you can't interact with at all. How will astronomy learn this? It's very difficult. And I sympathize with this fact, right? Because you have to have a reliance on tests. You have to be able to forecast things. And the other phrase I almost hear is garbage in, garbage out. Put garbage stuff in your simulator, you're gonna get garbage out. Well, the truth is, sometimes you can look really good physics and really good understanding in the simulator and get garbage out. All simulators are wrong. Rarely, they are somewhat useful. That's where a lot of the scientific community is. So I'm going to go through the ingredients of a spiral galaxy. How much time have I got? I'm talking slowly. Is that a good plan?
You go ahead and finish it.
Okay. So, what we need to contain our gas. So, it's very simple. We need a sufficiently dense, sufficiently massive object in the center. Something in the center, condensed material, will hold all this gas together. Okay? Because just like that star formulation, the gas will just keep expanding if you don't have anything in the center. So for Andromeda, the mass of the galaxy, the mass of the gas that we've got around it, is about 1 trillion solar masses, 1 trillion times the mass of the sun. It's got a black hole of 100 million solar. That's pretty big, it's pretty heavy. But it's only 0.01% of the mass of the gas cloud. So we don't need a lot of material there. Just got to be, 1/10,000, is that? Yeah, of the mass. Will do. So we've got, what else do we need? Well, we can't have all the gas, we can't actually have it touching that black hole, because the black hole will just suck it in and then we won't have a galaxy at all. So we have to have something to balance the gravity of the black hole. And this goes back to another Newton experiment. And it has to do with a cannon that you put up on a mountain. And it has to do with that model where things are colliding with one another. Well, if you shoot the cannon and you don't give it enough velocity, you'll sort of miss outer space and you'll collide with the Earth, and your cannonball will become part of the Earth. If I shoot it too fast, you'll have the escape velocity of the mass of the Earth, and it'll go off into outer space. But in between those, I can shoot it with enough speed so that it has this circular orbit due to angular momentum. And whatever it is that I shot out of the cannon can then orbit the Earth, provided it's not too dense. So how does this come about? Well, you really don't know how it comes about. It can actually come about in various ways, but essentially it involves, gas sort of moving at some speed past a black hole, and the black hole kind of captures it in an orbit, right? And that's angular momentum. And how far it orbits away from that black hole depends on how much angular momentum it has. If you look at a large mass, you can see that, okay, this close part of the cloud that'll come closest will have more angular momentum than this green dot over here. You'll start circling the black hole, and you'll end up with a cloud going around in a circle. The other way the cloud can be captured is it can be stolen from another galaxy that might have less angular momentum, or might have less mass, and it actually steals it. And that happens with really what happens when they collide. But then we get a little bit stuck, because some of that gas is going to be orbiting in a circle, some of it's going to be orbiting in ellipses, and then it'll be orbiting at different distances, and some of them are going to be orbiting out of the plane of other gas molecules, if you will. So we get a little bit stuck, and we need another force. And here we go. I need another force to organize this going around and around. And here's where I introduce friction to this whole thing. But before I do that, I'm going to suggest to you that the gas cloud forms not a sphere, like I showed you in that Newton model, but a torus. What's a torus? It's just a donut shape. It's a sphere with a hole in the middle. And topologically, a coffee mug, since it has handles and a hole in the middle, is a kind of torus. And it's got a, because it's not spherically symmetrical, it's got a gravitational field around it that's quite a bit different than a sphere. Again, if I'm right in the middle of the torus, I don't have any radial gravity because there's equal amounts of gas all around me. But as soon as I move away from the center, then this side of the cloud is going to give me some gravity. It's actually going to pull me out from the center. On this side, the torus is going to pull me in. So I get this gravity that kind of is positive because it's pulling me out from the center. And then in the torus, it switches from gravity that's pulling me in out here. Looking at the other angle, you get the gravity in this direction that's always pulling into the plane of the torus. Except out here it's a little bit spherical. So that is completely different from Newton's shell theory. But I think a lot of astronomers, not all of them, but a lot of them are applying Newton's shell theory to a torus. And it doesn't hold, which says that the gas molecule in the middle doesn't feel anything from what's outside. Well, in a torus it does. This will be important later. So what I want to do is, remember that myth that gas molecules are far apart, feel van der Waals forces. Well, the fact is, those van der Waals forces get very strong when the gas molecules are close together. Without these forces, right? Well, without collisions, we get something like the solar system. We've got our planets orbiting in a circular orbit. They never collide. They're always far apart from each other, and our one model applies. And if you know something about an idea that came out was, why don't we take all of our garbage, our nuclear waste from the atom, and let it go into the sun? Why don't we just put it on a rocket and put it into the sun? It's not a bad idea, but there's a problem with it. As soon as we got a rocket off the Earth, I think this is the Earth right here, as soon as we got a rocket off the Earth, out of orbit, it's still got angular momentum going around the sun. So in order to actually fall into the sun, you have to put a lot of rocket fuel and point the rocket opposite to the angle of revolution, and in order for it to hit the sun. It's actually very impractical. It's very hard to hit the sun. The planets have been trying for ages. They just can't hit it. We keep missing every time we go around, right? So what I need is something, if I wanted the planet to get closer to the sun, I have to put a force that slows it down. That's where friction comes in. Those van der Waals forces, although we're ignoring them, and you can ignore them for the planets, we have very little force in between them. They will make themselves jiggle by gravity. But in order to make those important, we have to look at when those little balls in the random walk, when they actually collide. Okay? So that model is all about the collisions. Real gases always collide. Even if they're sparse, they might collide less. But when they collide, these van der Waals forces act on those particles and make them a real gas. An ideal gas does not exist. It's always a real gas. And the argument that the molecules are far apart doesn't hold to say it's an ideal gas. Because as long as there's collisions, those forces will be important, and that creates friction. When those molecules collide, something funny happens. Even if the atoms are neutral, you'll see the electrons in some of the collisions might be perchance on one side of one of the atoms when they collide. And that will induce the electrons on the other atom to move to the other side. And now we've got positive next to negative, next to positive, next to negative, and we've got, hey, we've got electrical attraction between the two. The molecules actually come together. They're actually sticky to some point. Now, you need enough temperature, and some of the collisions won't work this way, but when these atoms stick together like that, their momentum, they can't, when they're stuck together, the momentum is averaged, right? Now, for neutral atoms, what generally happens is it only comes together for a little bit of time, and then temperature splits them apart. It's only a temporary stickiness, if you will. In other cases, the stickiness can be more important. In fact, you can form molecules if they get slammed together, right?
It's gonna need to go to questions fairly soon, Dave.
Okay, well, that's why I was asking how much time I got.
Yeah.
I'll zip through the rest, okay? Is that fair?
Yeah, about, 5 minutes would be great.
5 minutes, okay, I'll really zoom. So essentially, there's a little bit of love attraction when the molecules attach, giving them like sort of velocity, If you got one molecule moving another past another one, you'll see they'll end up moving more like another. And that's the friction that we're after. And that's what causes that friction that we see, and we call it viscosity. It's the inability for one molecule to just, or it's the difficulty one molecule has for moving past one another. It's the same thing if you're trying to pull a weight on the ground. It's got friction with the earth, and force doesn't equal mass equals acceleration because you have to keep applying force as you drag it along the floor. It doesn't ever let go. The other thing to note is that it creates heat, and there's a whole bunch of formulas that describe this. I'll skip this. But one thing, when you got friction, is the definition of wind. Here's a couple of pictures I've taken of planetary nebula, which are the gas clouds that are formed when stars die. And actually you can see the effects of wind in space. What might have started off as a somewhat spherical object gets distorted. This is upstream in the galactic wind that's moving this way. In this planetary nebula, this is the skull planetary nebula, the flaming skull, the gases are moving this way. You get this shape is effective viscosity. You also get that dispersion back here because it actually scatters the molecules eventually. But there's wind in space. Here's a molecular cloud. Dispersion is far less in this place, but we see lots of tendrils being eroded off this molecular cloud, which is mainly H2, if you remember, is being eroded by a wind going in this direction, made out of hydrogen atoms, not hydrogen molecules. The dust likes to stay where the gas is dense. I won't go too much into that. But that's why what we're actually looking at is the dust. But the dust is, H2 is actually invisible, so we figure out where the hydrogen really is by where the dust is. So now we've got friction and viscous drag to make our galaxy. So friction doesn't allow a differential in two concentric disks as they would rotate in a galaxy or something. And we can measure how much friction there is between disks rotating at different speed and then assign a viscosity. Whatever, am I taking way too long?
No, just gotta wrap it up in a few minutes, Dave.
Okay. So I did tell a fib that it was a torus, but it is a torus, but it's more like a disk because we organize all the orbits in a round circular way with a little hole in there. If the hole collapses, then material will fall into the star, but there we go. There are some galaxies that look like a torus. And here are the galaxies. Great. Going back to that gravity is very important. I'm going to skip this part. But if I've got a pendulum, maybe I should, I'm going to skip this part. A spiral shape is what you get when a pendulum has a friction force on it. I don't know if you can see this on the board. If you can see this on the board, is how a pendulum swings with no friction. Basically keeps swinging forever. If I make this the distance, plot that, versus the speed, and I start my pendulum at sort of this side, it will make a circle as it gains negative speed as it swings back this way, and then that'll be converted back into potential energy, and it'll end up over here, and then it'll start to swing backwards, it'll get some velocity in this direction, and it'll come back here. If I make it have friction and start it back over here, you'll follow this, the friction will take a little bit of the speed away, so when it gets back to the other side, it won't get as high as it did in the frictionless case. Then it'll swing back this way, and now it may only get here, it'll only get this velocity, and then it'll go up here, and then it'll form a spiral, and in the middle. So in nonlinear dynamics, friction, you see spirals all over the place. You actually see it in viscous material. When turbulence occurs, you'll see these little spirals form. The left is a picture of a star forming. The right is a picture of black holes. Right is an artist's conception of black holes with material falling in a spiral pattern in onto the protostar on the left or a black hole on the right. They're essentially the same process. Different scales, different substances, different things, but it doesn't take to a genius at saying the same forces are at play. Angular momentum, spirals, and gravity and friction are at play in both of those processes. And astronomers will admit that, okay? But in your frictionless, even if you admit to friction, and this is a really good slide, because it says, if I want to slow down, A moves the disk at A, the center disk, if it moves faster than the ring at B, it will try and slow down, B will try and slow down A, and A will try to speed up B to make them consistent, right? That's the friction. So this means that angular momentum is transferred from A to B. That'll make the disk at A move in, and it'll make the disk at B, it'll try and move out, and it'll try and separate from one another. And what that does is it'll make that separation, unless there's a disk C further out, that slows down B, and on we go. The only thing I didn't like about this slide is it skips the part that heat is created. This is this iterative process. And that's why astronomers don't really like this particular process. If I put some oil, you can see that a spiral sort of stress will happen in those rotating disks. Now, if I put a little oil in between at those stress lines in a spiral, the spiral will open up. And we see this in nature. I'm going to show a couple of pictures of flowers opening. What the flowers do is they put some air in between the petals that are wound up in a spiral, and that sort of lubricates the surfaces between the petals, and the flower can just open up into a beautiful spiral.
I want to see if people have questions. This might be a good time to see if anybody has any questions.
Running out of time. I don't have too much more time. Is there any questions people have?
Are you gonna finish with a big bang?
Not quite. I'm going to finish up with the galaxy. What's people want? Do you want to go for tea and coffee, or do you want to take 5 more minutes? Am I imposing?
Well, I think if we could wrap up in 5 minutes, that would be
Okay.
yeah.
So the astronomy argument against this sort of model is that they say, okay, if I put stars in the galaxy, the first mistake is they define the galaxy arms by stars. They say, okay, Dave, you're saying the galaxy moves like this on the left-hand side. But the stars don't have any viscosity. And I agree, the stars don't have any viscosity. They're stuck in a paradigm where the stars are creating the spirals. Because they say, if you just put stars in, it'll wind up. Okay? And they call this the winding problem. So what they then say, let's get this. They say, this is made up, this is something called density wave theory. And they suggest that those spirals aren't real. They're really these gravity waves caused by stars ending up in a traffic jam. It's sort of a, I don't like it. Instead, and I sort of said, okay, well, I'll run with this and say, okay, they're gravity waves, but that should end up with something called an Archimedes spiral, and I can show that the gas molecules within a spiral are not actually orbiting the center of the galaxy. They are material, and I'll show that in a second, but a free body diagram shows that they can exist without winding because the individual molecules are not orbiting the center of the galaxy, as you might think. Second thing is like this galaxy here, it has parts of its arms that are sticking straight up out of the galaxy. Now, without going into explaining how this can happen in a friction world, it can't happen with the gravity waves. They have to be parallel. If they existed, they would have to be parallel. Instead, a spiral pattern is better explained by just saying they are different phases. They are hydrogen existing in different phases. They have different viscosities. Those arms have a high viscosity. H2 is a bigger molecule. It has more van der Waals forces. It's got higher viscosity than the lubricating agent, which is the individual hydrogen molecules in the outside. They both show the same thing. We can see those two phases interacting in areas where stars are falling upon the molecular cloud. The stars are actually making, I'm going to skip these, these are the pretty diagrams. The stars are actually making H2 going to H+. I'm not going to go through this, but it's on the video. If we go into a hurricane, we can see the same things happening. Hurricane's a spiral. It's got two kinds of phases. It's got a wet, water-rich component, and it's got a dry gas that's heavier, it's colder, and it circulates, the wet, warm gas circulates up from the ocean, and then it cools off, it lets off all its water, and it drops down. So heat is driving a hurricane. Different phases form a spiral. The exact same thing, a little bit different configuration than a spiral galaxy. I'm just going to get through this next series of slides because it puts it all together. A galaxy is really a pump. We make pumps, and not by accident. We didn't look at galaxies to make a pump. We actually made a pump so that it would be most efficient. Now, if you bear with me for a second, the white arrows represent the gaps in between the galactic arms. And as the arms turn, it actually pumps that gas to the outside. In the case of the pump, those arms are made of steel. In the case of a galaxy, those arms are made of that H2 spiral material. Force, opposite direction, steel can resist it, but gas can't. So the spirals are actually gas moving in towards the center. So we've got H2 gas moving in towards the center, I've taken the motor away and I've replaced that with a black hole. Okay? And that's how it goes. Hydrogen that's formed from H2 by the stars in the galactic arms enters the gaps between the arms and actually expands because it gets heated up by the stars and drives the whole turning of the thing. That's the engine of what's going on. So it's the energy that's given off when hydrogen molecules are turned into hydrogen atoms. The energy that's absorbed from the stars and turns into hydrogen atoms. Some of the spirals aren't so well defined because the clouds can move between the stars. Here's some infrared images that focuses on the dust. And we can see the dust actually moves between the spiral arms as well as the hydrogen atoms through erosion, because there's lots of turbulence going on, and that erodes that material. And you can actually see, these are infrared images of galaxies taken by Jacob. You can actually see how that dust and H2 is actually moving between the arms. Back to our torus arrangement, the gravity actually can be made by a series of concentric toruses. Here we go. Oh, my hand was eating up. Concentric toruses can make the gravity periodic with radius. It's actually periodic in the angular direction, too. Now, indeed, the stars don't have viscosity, totally agree. But the stars are subject to the gravity that the galaxy creates. And so we get this dance where the stars aren't following the spirals necessarily. They're doing their own thing according to this periodic gravity, slowing up and speeding down. And so they're actually not really flowing the gravity. They'll feel hard gravity, heavy gravity, or lots of gravity when they're in proximity to the arm, and they'll actually move in with the arm, just not along the spiral. But then when they're in between, they'll feel less gravity. And then their angular momentum will take them out. So they're moving in and out. They're slowing down, moving faster as that gravity of the spirals jiggles them around. And we can see this jiggling. And these are plots that were originally used to justify, 2 slides. Originally used to justify dark matter. Because they said, well, the spiral disk is real. There's no spiral arms really, they're just gravity waves. And here's how we expect the rotation speed of the stars to vary with distance. And they said, well, here are my measurements. And they can measure the speed of material by something called redshift. The stars last out to here for this galaxy, and from Andromeda they last out to here. But beyond that, we can actually, there's hydrogen atoms which they can identify. They can see in infrared, but they can't see hydrogen molecules. You have to trust me on that. I'll get into it, but we don't have time. Here is the actual speed. Well, that's totally consistent with this kind of gravity field. So what it means is I don't need dark matter to make the spiral velocities, the velocities look like this. I just need spiral gases. The second thing, which no one seems to mention, is that if you look at this, you'll see even within these error bars, which I wish they'd get rid of because there's lots of time since these graphs were made to reduce these error bars, but nonetheless, you can see there's this undulating behavior, and you can really see it in the Andromeda galaxy. You can't see it so much in here because the spirals are so tight and they're so small, but out where the spirals are big, as you can see there's a lot of hydrogen gas well out. So these galaxies are really much bigger than they appear. Now I can't prove that there's no such thing as dark matter, no more than you can prove that unicorns can exist. But it kind of leads you in that direction. So here's my conclusion. Take a multidisciplinary approach because it can lead to a greater understanding of the physical processes. I'm an outsider. I'm not an astronomer. I didn't go through the standard education that an astronomer goes through. I can see blind spots. Not that I'm smarter, it's just that I come from a different perspective, right? Always use your mind because simulators can't hold these multiple universe views at the same time, right? And if you're able to hold multiple views, you can slay unicorns and turn them into black swans. Thank you so much for your patience. Sorry to keep you over time. Let's have some fun over at the center.
Are there any burning questions?
I'll be over there.
Yeah, all right. Well, David, thank you very much.
I apologize.
Just on behalf of RASC, even though you are a member and believe in me. Oh, that's okay, now you have 4.